All right, let's cover Unit 7, which is reaction rates and equilibrium. Starting off with number 1. What is activation energy? Activation energy is the energy needed to start a reaction. So energy needed, so required to start reaction. And the abbreviation for reaction is RxN. Number 2. What is the activated complex? It is the position right before your reactants become products. Become products. What are the 4 things that make a chemical reaction go faster, and why does it make it go faster? Number 1, concentration. By increasing concentration, you're increasing the frequency of collisions because there's more things to collide. Number 2, temperature. By increasing temperature, you're increasing the collision speed. Number 3, particle size. By decreasing particle size, you're increasing surface area. Number 4, catalyst. Catalysts lowers the activation energy. How does catalyst affect a reaction? Well, we just talked about that. It lowers the activation energy. How can you use a balanced chemical reaction or equation to determine the rate of a chemical reaction? Go ahead and put a star next to this, circle it, do whatever you need to remind yourself that this is a key point of the unit. You cannot use a balanced chemical equation to determine the rate of a chemical reaction. The only thing that determines the rate of a chemical reaction rate is only determined by experimental data. Experimental data. All right, key point. Number 6. In the following reaction rate, K and the concentration of A, concentration of B to the third, what is the order of A? So the order is the exponent, and if you don't know already, the exponent, or if nothing is there on the exponent, there's an invisible 1. So we know that the order of A, the concentration of A, is first order. The order of B, we look at B, we see a 3 as our exponent, you just bring it down, third order. What is the overall order of the reaction? Overall order, all you're going to do is you're going to add these two. So 1 plus 3 is 4. So your overall order is going to be fourth order. All right. Let's take a look at number 7. Consider the energy or reaction energy diagram shown. How many elementary reactions there? How many intermediates are there? So understanding this is important. Elementary reactions are a single step reaction. So single step reaction. Intermediates are going to be a single step, same thing. So I'm going to write it out. Single step reaction. But products are used for another reaction, another elementary or intermediate reaction. So the products are going to eventually get canceled. So determining elementary reactions, you have to understand that elementary is related with the crests. So the crests of the graph are going to be the highest peaks. So you can see there are 3 highest peaks. So these are all elementary. So we have 1, we have 2, we have 3. So there are 3 elementary reactions. Intermediates are troughs. So the troughs of the graphs, you can see there's 1, there's 2. So these are intermediates. There's 1, There's 2. There are 2 on the graph. Indicate on the graph the activation energy for the reaction. The activation energy is the energy needed to start the reaction. That is always going to be our highest point. So let me just draw the graph. So the activation energy is going to go from our starting point to the highest point. This right here is going to be our activation energy. And we have indicated on the graph. The delta H of the reaction is the change in enthalpy. That means that this is going to be, note to the side, delta H is going to be the change in enthalpy, or the heat added or removed from the system. In system. All right, so the heat added and removed from the system you can calculate very easily by looking at this ending point and the starting point. So the starting point is there, and the ending point is here. So this right here is going to be our delta H. And we have indicated on the graph. And based on this equation, you can kind of see already from our delta H, we started with this much energy, and we slightly went up to this point in here for the energy. That means that we have heat entering the system, En, therefore it is endothermic. Let's make a note. Heat enters. All right. Let's move on. Questions 10 and 12 are based upon the following reaction. We have heat plus NH3, which is, we're going to make a note here that says ammonia. And we have H2O water, and this produces NH4, which is ammonium. And we have hydroxide right here. Write the equilibrium constant expression for the reaction. Equilibrium constant reaction, we're always going to have our products over reactants, which will be our products well, let's just clear that circle though. NH4 plus products OH minus, and over our reactants, which is NH3. The reason why we are not including water or heat is because heat is a numerical value and water is liquid. We only include in our K equilibrium constant expression the aqueous gases. So NH4 is aqueous, hydroxide is aqueous, NH3 is a gas. We only include gases and aqueous solutions. And so this is going to be our equilibrium constant expression. Number 11. If the equilibrium constant for this reaction is 1.8 times 10 to the negative 5, what are the equilibrium concentrations of the ammonium and hydroxide ions if the equilibrium concentration of ammonia gas is 1.2 molar? Which side is favored, the product or the reactant? We can answer this part right here and say that the favoring occurs with the reactants. Favors reactants. This is because our equilibrium constant is K equals 1.8 times 10 to the negative 5. So if K is greater than 1, it is going to favor products. If K is less than 1, it is going to favor our reactants. Since 1.8 times 10 to the negative 5 is smaller than 1, this is smaller than 1, it is going to be favoring our reactants. All right, so if our equilibrium constant is 1.8 times 10 to the negative 5, we can just straight up grab what we wrote here and put it below. So 1.8 So K in this scenario is this, and this is equal to this. Therefore, 1.8 times 10 to the negative 5 is equal to the concentration of NH4 times the concentration of OH all over the concentration of NH3. So this and this we do not know. So we're going to call those both x's. But in this scenario, we do know NH3 because they gave it to us as 1.2 molars. So x squared on top, since we don't know what this is, and they're multiplying each other. So x times x is x squared. And below we have 1.2 molars. And multiplying this to this, we're going to get x squared alone. We are going to get x squared x squared equals 2.16 times 10 to the negative fifth square root on both sides, and you're going to get a single hand x equals the concentration of NH4 plus equals the concentration of OH minus, which is going to be equal to what we square rooted earlier, which is 0.004647, which I'm going to round and convert to scientific notation, 4.65 times 10, I'll write it a little smaller, 4.65 times 10 to the negative third molars. And that is our final answer. And this applies both to the concentration of NH4 and hydroxide, because each is seen as X. Alright, what will be the effect on the equilibrium position if the OH ions were added to the system? So we're increasing the concentration of OH minus. So if we increase, the rule is that we have to shift the equilibrium to the other side. We shift away from the increase. Therefore, since this is on the right-hand side, the product side, we're going to move to the left-hand side. So we're going to have a shift left. If the system was warmed, that means the concentration of heat will increase. Concentration of heat increases. When we increase, we shift away. It's on the left-hand side, reactant side. So we move to the right-hand side. We shift right. What about pressure? Now, pressure, it's a little special. So for pressure, we only consider gases. Only consider gases. So in order to do this, we have to look at our equation. What do we cut out? So if you have heat, heat is not a gas. So we cut off heat. NH3 is a gas. Water is a liquid. NH4 is aqueous. We cut it off. And hydroxide is an aqueous. So we cut it off. So on the left-hand side of the arrow, we have 1 mole. So there's an invisible 1 in front of the NH3. We have 1 mole on the left-hand side. 1 mole on left. And on the right-hand side, we have none. 0 mole on right. For pressure, we shift to the side with less moles if the pressure increases. So if pressure goes up, shift to side with less moles. Therefore, we have to shift towards the side with the less moles. We have 1 mole on the left, 0 moles on the right. We have to shift to the right. Shift right. All right. And if more water is right here, if water is added to the system, it's a liquid. So then if a liquid is added, we have no change. Because water is liquid, it is not a gas. So we only have to take into account gases. So if water is a liquid and it's added to the system, it will not bring about change. All right, let's try questions 13 and 15, or 13 through 15. We do not have a question 15, but let's try 13. So we have calculating the concentration of the Pb2 plus ion on a saturated solution of PbS. So we are given the KSP, solubility the solubility constant. Okay, so the equation for KSP is going to be KSP is the same thing as our equilibrium constant expression. So KSP equals the concentration of our products over reactants. When we take a look at our products, we have aqueous, aqueous. When we check out our reactants, we only have a solid. Solids are not included in our solubility product constant. Therefore, we only have to write the products for our KSP. So concentration of Pb2 plus times the concentration of S2 minus. That is our KSP. We are given the numerical value for KSP. We can write 3 times 10 to the negative 20 equals, and if we see each one as x, we have x squared. Square root on both sides to cancel this squared, and we have um, x equals 1.732 times 10 to the negative 10 as our x. And since our x is equal to the concentration of Pb2 plus and the concentration of S2 minus, that means that this 1.732 times 10 to the negative 10th is going to be our concentration for the Pb2 plus ion. That is your final answer. Use the given thermodynamic data for a reaction to determine if the reaction is spontaneous. We are solving for delta G. If delta G is a positive, not spontaneous. If negative, spontaneous. All right, so the equation we're going to use is the Gibbs free energy equation. Delta G equals delta H minus T delta S. This is not given on your test. You have to memorize it. All right, let's define each of our variables. Delta G is our free energy change. Free energy. Uh, so that is going to be Gibbs free energy. We have delta H, the heat of reaction, Rxn. We have temperature, of course, in Kelvin, and change in entropy. In entropy. All right. So with this information, we have everything, but we have to look at and make sure they're all in the same units. We want temperature in kelvins, so we convert this using our equation. C plus 273 equals Kelvin. So add 273 to 25, and you get 298 Kelvin. And this is in joules, but we want it in kilojoules. So all we got to do is divide it by 1,000, and you get 0.256 kilojoules per mole times K. With this, now we can solve. So all we're going to do is plug in for delta G. Delta G equals delta H, which is 11.9 kilojoules minus 298 times 0.256. When we solve for this part right here, we're going to get 11.9 minus 76.288, and our delta G is going to end up as negative 64.388 kilojoules per mole. Since there's a negative, we know that it is spontaneous. Spontaneous. That is our final answer. And we are done.